Let's take a look at a problem where we've banked the turn, but we'll ignore friction in this case. That makes it a little easier. And so a bank turn is when you turn the road surface in toward the center of the circle. Here's a velodrome, which is where they race bicycles. And here you can see the racetrack is tilted for that purpose. Here's a close-up showing some bicyclists on this obviously banked turn. What we want to know is how fast could a car go around a bank turn if it had a mass of 1,000 kilograms, the radius of the turn was 20 meters, and the angle of bank is 20 degrees. So how fast could the car go without slipping out or falling in? And so an overhead view will help. And so here's the car negotiating the turn, but this shows the radius of the turn. But to get a better perspective, let's look from behind, and the car is moving away from us. And so it would look like this. We'd see the banked turn, where theta is measured from the horizontal here, and this would be the car on the turn. And so the car is moving into the page. This is not a block sliding down a ramp. This is a car on a banked turn. And so let's draw a free body diagram. We have weight acting down and the normal force acting perpendicular or normal to the surface, as it always does, and again, no friction in this case. And we put our coordinate system so that one axis is in the direction of the acceleration. The acceleration is toward the center of the circle, which would be horizontal, so the x direction is where we have acceleration, no acceleration in the y direction. So let's take a look at the y direction first. Some of the forces in the y have to be 0, and here I have a component of the normal force in the y direction. And so here's the y-axis. This would be angle theta, and so the normal force has a component in the y direction and a component in the x direction. And the y component is adjacent to the angle, so it's n cosine theta, and it's up, so it's positive. And then the weight is all in the negative direction, so minus mg equals 0. So we get the normal force is mg over cosine theta, which might puzzle some people, but remember, this is not a block sliding down a ramp. The normal force is not equal to mg cosine theta as it would be for a block sliding down a ramp. In that case, a block sliding down a ramp, there's no acceleration in the direction of the normal force. But in this case, since the acceleration is horizontal, there is a component of this acceleration in the direction of the normal force, and so that's going to make it different. It's going to be greater than if it was a block sliding down a ramp. And so this is an example where you don't want to memorize an equation, you want to derive it, and then you can clearly see it has to be mg over cosine theta. And in the x direction, we do have acceleration, but it's a centripetal acceleration, so it equals v squared over r for uniform circular motion. And the sum of the forces in the x would be the other component of the normal force. So the component of the normal force in the horizontal direction is what's causing the car to turn. So n sine theta, that's why we bank turns. So the normal force helps the car make the turn. And so n sine theta is mv squared over r. And we can substitute what we got for the normal force, or if you hadn't solved for it yet, you could go and get it then. And you get mg over cosine theta times sine theta. And if you remember, sine over cosine theta is tangent theta. So if you simplify and solve for v, you get v is the square root of gr tangent theta. We put in our values and we find out that the car is going 8.4 meters per second. If it went faster than that, it would slide up. If it went slower, it'd slide down. If you want to see if you know how to do one like this, what about if I told you it was going 8.4 meters per second, what would be the bank angle that would work for that? Now you know the answer. See if you can start from scratch, draw the free body diagram, derive the equations, and find out that theta is 20 degrees. Good luck.